Hello, and what do you think about this question? This is a check your channel question. If you press the answer and it blinks green, you're all set. And of course, we should apply our knowledge about the work done for an object traveling in space to this situation. It's a rotational motion. So we need to make up an object which is kind of traveling in space. And in that case, when we look at that object, we can answer this question. So we can just look at, let's say, this part of this wheel. Is it moving? Basically that's it. So keep pressing 1. Of course, there is some work done to start. Yeah. For example, the motor, we have to yank it, and if we want to spin a roulette, we just have to compare two situations: the initial situation, rest; final situation, motion. Every individual part of a wheel is moving. So if we break it down into small parts, into small individual parts, this one, this one, this one, this one, well, it will take forever to draw all parts. Each, of course, is moving. It's a particle, it has a kinetic energy, so to make it move, we had to do some work. And turns out it's very kind of easy to prove that for rotational motion, the work done by a torque equals this. It's basically same structure, force times displacement. Instead of force, we're using torque, which now is responsible for rotational motion. Instead of a linear displacement, we use angular displacement. And again, in general, we have only, for rotational motion, we consider we have only two options. The torque and velocity might both be, well, clockwise or both counterclockwise, so parallel. Or angular velocity might be opposite to the torque. So that's what we call anti-parallel. So for rotational motion, this angle is either 0 or 180, which means this cosine is either +1 or -1. So if you have several torques acting, like here, my force applies a torque, and force of friction here applies a torque. And my force, well, see, the torque relative to this axis from your perspective is clockwise, and the velocity is clockwise. So that's what we call parallel. Yeah. And if you remember, for the clockwise motion, we used a direction, we called it into the screen. So we can say angular velocity of this wheel points into the screen, the torque due to my hand points into the screen, so same direction. The angle between these two directions is 0, cosine of 0 is 1. So this torque does positive work, but friction opposes motion. So right here, the friction points to the right. Relative to this axis, torque due to friction is counterclockwise, but angular velocity is clockwise. So angular velocity clockwise into the screen, frictional torque counterclockwise out of the screen, they opposite to each other. Opposite means this angle equals 180, cosine of 180 is -1. So friction does negative work. Well, friction always does negative work. Someone still pressed 2. Don't do anything today. Okay. Well, the answer is yes, does. Does. Well, in this situation, when actually the rope speeds it up, the rope does positive work, and if we had any friction acting on this wheel, that friction would be doing negative work. It doesn't matter if it's a torque does work or force does work, it's work, so the unit is the same, joules. And now, as we said, each individual part of that solid object has a certain kinetic energy. So if you want to calculate the kinetic energy of the whole wheel, you just need to add all those energies. Okay. So when we add them up all together, we get the same coefficient as we had before. We called it the moment of inertia. So for the solid object making rotational motion, if we want to calculate kinetic energy of the whole object, we just have to use this expression, 1/2 inertia times speed squared. It's the difference is everything related to rotational motion. That's not the mass, that's the moment of inertia. That's not the speed, that's the angular speed. But the same relationship between kinetic energy and work stays. If we change kinetic energy final minus kinetic energy initial, that has to be equal to the total work done by all torques So let's do this problem. What amount of work has to be done to speed up a disk from rest to 100 revolutions per second? So we are looking for the work of that particular force. We are assuming no friction, of course, no other force is acting. So we can apply, this is the work kinetic energy theorem, but for a solid object making rotational motion, we just have to use, well, different expressions. For kinetic energy equals this. The initial kinetic energy was 0 because it starts from rest. Nothing is moving, no kinetic energy. Now, and that has to be equal to the work we are looking for. So we need to know what? The moment of inertia. The moment of inertia depends on the shape. So it's shape dependent. That's a disk, right? Yes, yes. So for the moment of inertia of the disk relative to the axis which goes through the center of mass, the moment of inertia equals 1/2 times mass times radius squared, 1/2 times 5 kilograms times centimeters have to be converted into meters squared. And well, a kilogram, a meter squared. And now we need to know the omega. The omega is the angular speed, and it is 100, that's final value, 100 revolutions per second. So, question? Can we use it? Because we have to convert it into radians. That's it. 1 revolution is equal to 2 pi radians. That's it. So these are our numbers. We just have to use these numbers, plug them, and that gives the amount of work done. Actually, we could have make even the next step. That's a disk. And we assuming nothing else is acting on it. So that's some kind of a force applied. In this situation, this amount of torque should be equal to what? Should be equal to the torque. This amount of work should be equal to the torque times angular displacement. We have to remember that also should be calculated in radians, not revolutions, not degrees. That's what people sometimes forget. So if we knew time, for example, or force, yeah, because torque also equals force times the lever arm, and for all situations like that, the lever arm is just equal to this radius. So we could find more variables here. For example, if we knew the tension, we could calculate the torque, and after that, we could calculate the angular displacement. And if we know angular displacement, angular velocity, we can calculate angular acceleration if we want to. Well, lots of things, yeah, using all knowledge from the past. So this is the same slide. Now, I want to talk about a different quantity. So we use an analogy between linear motion and rotational motion. Linear motion has kinetic energy, rotational motion has kinetic energy. Work done during the linear motion, work done during the rotational motion. And now another quantity, momentum. We used the law of conservation of linear momentum to describe possible collisions between cars, for example. And for rotational motion, very similar reasoning can be applied. So this is the Newton's second law, however, not for translational motion, for rotational motion. Net torque equals moment of inertia times angular acceleration. Exactly the same calculation, we just use different letters. Instead of M and the A, we use I and alpha. And so the result, of course, is also the same. This is what we used to call the impulse. This is what we used to call momentum. Well, when we talk about rotational motion, this part has no name. It's just a product, net torque times time. But this part has a name. Now we call it angular momentum. This product, instead of mass times velocity, now this product is equal to moment of inertia times angular velocity. We call it angular momentum. And for the angular momentum, we use a new letter, a new variable. We call it a capital L, angular momentum. So if net torque is not zero, the angular momentum changes. But if net torque is zero, the angular momentum doesn't change. That's it. So for collisions, for example, when net force is zero, the linear momentum of the whole system stays the same. Now we make exactly the same conclusion. For rotational motion, lift with your legs, not your back. We know why. For the rotational motion, the angular momentum also stays the same when net torque equals zero. So for example, in this situation, The system is composed of two objects, object number one, object number two. If I release it, it falls, and that's what we call collision. But the total angular momentum of the system has to remain the same. So when I let it go and I release it and it falls on this disk, what do you think is going to happen to the angular velocity of this disk? The disk is spinning at angular velocity initial, and I hold a heavy ring above it. That's what we call before the collision. After the collision, the ring is attached to the disk. That's the final angular velocity. The angular momentum is equal to this, and the angular momentum of the system has to be constant. So the final angular velocity will be related to the initial, and when we have two numbers to relate, we have only three options: number one, number two, number three. Nothing else exists in math. So please choose your answer. I'm going to look at it from above. Oops. What's happening? Oh, okay. So choose your answer, write it down so you wouldn't forget. Keep pressing because I'm switching to the camera. You will not see this slide anymore. A metal hits a metal, what do you expect happen? When two metal parts, heavy parts, hit each other, what do you expect to happen? Very loud noise, of course, so be prepared. Actually, too fast. If it slides off, that might be dangerous. So. That's what I like about this, especially in the morning class or in evening class. So what did you observe? What about the velocity? A little, yeah. So it has to slow down. We can prove it, and we will, in a half of a minute, we will prove it just by using the law of conservation of angular momentum, that new law which we know now. First of all, you see, the key word people might forget sometimes is this, system. This system is composed of two objects, right? So there is the angular momentum number one, initial. There is angular momentum number two, initial. And that should be equal to the moment of inertia of the disk times initial angular velocity. And that should be equal to what? Zero, because it wasn't rotating. So the initial angular momentum of the system is equal to this. The final angular momentum. Well, now they travel together. So the angular momentum number two has to be equal to, well, they travel together. But now instead of adding masses, we have to add I's, rotational inertia. So there's going to be the same moment of inertia for the disk, but plus the moment of inertia for the ring times the final angular velocity. And the law of conservation of angular momentum tells us that final angular momentum of the system has to be equal to the initial, and we can solve it for the final angular velocity, which is going to be equal to this ratio times the initial angular velocity. So you see, it actually absolutely doesn't matter if it's a disk or a sphere or wherever, because this fraction always less than 1. Because the numerator is less than the denominator. We are adding some positive number to the numerator. So, any questions? This is just an illustration of the law of conservation of angular momentum. So, good, good, good. And there are, I'm not going to ask this question, there are many, many classical experiments about the law of conservation of angular momentum. So this is a classical problem, and there's a classical demonstration which I'm not going to do because it's classical. You can Google it, it's everywhere. A person's standing on this stand, spinning up, and holding 2 dumbbells, and if you move the dumbbells closer or further away, that affects your velocity. How? Well, that's exactly the same question. If you're, so what's happening here? She moves arms closer. So she doesn't change the mass, but she does change what? By doing this? The mass stays the same mass. What's different? No, the center of gravity actually also stays the same because everything's symmetrical. What's different? Inertia, moment of inertia, rotational inertia. Mass distribution changes. As we know that if we move away objects from the axis of rotation, inertia rises, goes up. If we move it closer, inertia goes down. So in this situation, this variable goes down. To keep the product constant, that variable goes up. So she will spin faster. If you ever watched, ice skating competition, they do it every time. Close the hands, spin fast, move away, slow down. There are other experiments related to the application of the law of conservation of angular momentum. So this slide shows some of them. This is that classical experiment. This is the person with dumbbells and moving closer or further away. This is another not classical experiment. That's mine experiment when I drop the ring. Now, this is also classical experiment. And this experiment I want to do. To do that, I actually need this wheel. It's a heavy wheel. And I prepare the next experiment. This experiment has a name, a dying star. And you may have noticed I like trying new things. I've done this experiment before, but I've never done it on a table. So the shadow will be captured. So what do I want to do? I want to spin it. Now I want to And now I want to turn it. What do you think is happening? And why? Well, the law of conservation of angular momentum. I started from the angular momentum equals 0, well, relative to the vertical axis. So now, to compensate the momentum of the wheel, I have to rotate in opposite direction. Now, to compensate the momentum of the wheel, I also have to rotate in opposite direction. So pretty neat, huh? All right. The hardest part is get out of this. So, oh, you're always in a dangerous zone, you know. And the dying star, I need a large space, so that's why I also do it here. This is a star, neutron star. They spin, and actually they beam X-rays, you know, and that's how we actually know a lot of things about space, how vast it is. But when it dies, eventually it's getting smaller and smaller and smaller. And it spins faster and faster and faster, exactly like the ice skater now. Oops. Twice. Almost died today. Well, moving on. Rolling. Finally, this is the motion, the most complicated motion. Yeah? This is how it looks like. It's a combination of both. So this is what we call translational motion, or linear motion. This is what we call rotational motion. So rolling is a combination. First of all, what is the reason for this wheel to roll? What force does make it spin? What do you think? Friction. If that would be absolutely frictionless surface, like icy, oily, it would be traveling just like that, just purely translational motion. So for rolling, friction is important, but that's not the friction which slows it down. That's what we have to understand. So when an actual wheel rolls, car wheel or bicycle wheel, doesn't matter, we talk about two different frictions. There is friction which is responsible for spinning, and there is what we call resistance. So in this class, in our physics, we ignore resistance. We only, resistance could have happened if it was moving like this. So it was also, well, in this situation, it was also slightly sliding. So, slipping, that's what we neglect. No slipping, no slippage, no sliding. And in this situation, this friction actually is static friction. This is this point at the bottom instantaneously not moving relative to the ground. Come on. And, well, This is not a new situation. It's just a combination of two old situations. So if I ask you, what do we know about translational motion? You tell me one word. What do we know about translational motion in one word? Everything. And now, what do we know about rotational motion? Everything. Everything plus everything equals everything. So what do we know about rolling? Everything. Now, this slide is about terminology. People say, wheel rolls with speed. Which speed do they mean? Because if it rolls, every part of this wheel actually has different velocity. So when they say the speed of the wheel, they mean the speed of the center of mass of this wheel. This point travels horizontally. So when they say the speed, they mean speed of the center of mass. That's it. When they say acceleration, they mean the acceleration of the center of mass. But what if we ask about the speed of this red mark relative to this axis? Imagine that you are sitting here and you're looking at the rim of this wheel. What do you see? Pure rotational motion. So relative to the center of mass, that's a purely rotational motion. For rotational motion, the angular velocity and linear velocity are related. And the last and very important statement, if there is no slipping, in that case, well, look at this, at the red mark. If I make one whole revolution, right here, the distance traveled by this red mark is equal to 1 circumference. But the distance traveled by this handle, by this center, is also equal to what? The same circumference. Exactly same. Imagine that it's like a tape rolls off. So the distance traveled by this point relative to this axis is equal to the distance traveled by the center relative to the ground. If distance is the same, distance over time velocity is the same, velocity over time acceleration is the same. So the center of mass of this wheel has exactly the same linear variables, values, of the linear variables related to the center of mass of this wheel are exactly the same as the values of the linear variables of this point. So if this wheel travels 1 meter per second, that means this mark also travels 1 meter every second. Let's solve this problem. Let's solve this problem. So you have to solve this problem. You have to open the notebook, read the problem. This is what is happening. The wheel rolling. And that's, well, this bicycle wheel, what do we know? We know its diameter, 80 centimeters in diameter. And the speed, that person who rides a bicycle can read the speedometer, 18 kilometers per hour. So the question is, how many turns does this wheel make for half an hour? 30 minutes is a half an hour. If you need help with some equations, you should raise your hand and ask Otherwise, you just write them down, plug the numbers in. And I just want to give a couple of advices about units, because speed is in hours this time. 30 minutes is easier using the hours again. Now, the diameter we probably should convert into meters, and the speed we also should use in meters, 18,000 meters over an hour. So that's the last 10 seconds. You can see the slide. Use it. You can talk louder. You can sing if you want to. And after you finished your work, you can use your clicker. Did you press? What's your number? What's your number? That's not a number. If you say 1.29 times something, that's not a number. That's a product of two numbers. So what's your number? Somebody, give me your number, please. What's your number? I hear 3, then 5, 8, 1. 3,581. Okay. Is it yours? No? What's yours? I don't know if it's right or wrong yet. Well, of course you work together. No? Well, okay. This is a question mark. It's either I did or didn't, right? That may be. Yeah. Okay. Well, this is, there again, that's a physics problem. In physics, every problem can be solved using different approaches. Final number will be the same. So, what I did, I used the fact that the distance traveled by the center of this wheel will be equal to the distance traveled by any single point about the axis. So this distance traveled equals the speed times time. But this, because it equals the distance traveled by this point, and one whole revolution is equivalent of a circumference. So if we know the total distance and we divide it by the circumference, that gives us the number of turns. That's what I did. But also, it could have been done using angular displacement. If you have calculated total theta, angular displacement, and divided by 2 pi radians, that should give you exactly the same result. So this is basically, again, to strengthen our connection between rotational motion about the axis and translational motion. Okay, everything's gone. Just gone. Anyway, the number is correct. So, what about kinetic energy for a rolling object? Well, because the rolling is a combination of two motions, a translational motion of a center of mass and the rotational motion about the center of mass, the kinetic energy of the rolling object is equal to the sum of two kinetic energies. The kinetic energy related to translational motion, we just have to remember this variable v represents the speed of the center of mass of that wheel relative to the ground. And this term now represents additional kinetic energy due to rotation. So this is the rotational kinetic energy. So for the rolling object, we should add them up. That's it. And for the rolling object, the work kinetic energy theorem, of course, is applied, of course. And it looks like this. Same. And we just have to include all possible work done by forces and torques. If there is no resistance, again, without that friction, without that static friction, there is no rolling. So, but that friction doesn't do work because it's static friction. If there is no resistance, in that case, mechanical energy doesn't change. So, in general, we should have added that term, potential initial plus kinetic initial plus work done by friction, or we called it non-conservative forces, should be equal to potential final plus kinetic final. That's what we used to call mechanical energy. However, under this condition, no resistance, this term equals 0. Mechanical energy of the rolling object doesn't change. For example, if you roll a ball down a ramp, you can apply the law of conservation of mechanical energy in this form. You just have to remember that kinetic energy here, this term in general, also includes two terms, two parts: kinetic energy translational and kinetic energy rotational. That's it. Well, a better slide of what I just said. Why is it 2/5? Well, a ball is a kind of sphere. Yeah? If it's a solid with uniform density sphere, 2/5 mass times radius squared. And this is what I want to ask you. Oops, shoot. You have to use your imagination. On Friday, I will do that experiment. There is a ramp. There is a piece of ice which slides down with no friction. Instead of ice, of course, we just use a regular cart with tiny wheels, which are almost frictionless. And there is a ball which rolls down the ramp. And the piece of ice which slides down the ramp. They have the same mass. And of course, when two objects travel, we let them go, we release them from rest simultaneously. They reach the finish line eventually. And we have only three options to choose from. The sphere wins the race. The cart or that sliding piece of ice wins the race. Or it's a tie. All right. It's time to start scaring you. The best approach to this situation is not actually imagining what you're told to imagine. A cart sliding down and a sphere rolling down. The best approach is to imagine two spheres. One sphere slides down on the icy surface. So it doesn't roll, it just slides. This sphere represents this cart. But there's another sphere which rolls down. So one sphere which slides down, just slides, and the second slides and rotates. What requires more inertia, just sliding or sliding and rotating? So depending on your answer to this question, you should answer. What did I do? What did I do? Okay, it's gone. Well, anyway. So, of course, we can just solve it. But again, if you just imagine two situations, the ramp, a spherical object which doesn't roll. Just a second, doesn't roll. So the inertia is due to the mass only. And a spherical object which rolls in addition to sliding. So this requires more inertia. More inertia, it's speeding up slower, so it reaching finish line last. And this frictionless situation, cart or whatever it is, that object reaching finish line first. Okay, I'll pick up from this slide on Friday. Thank you very much, and I'll see you soon. You know where, and you know when.
Needs more inertia. What does it mean by needs more inertia? How
This is how you calculate kinetic energy.
Yes.
So if you have no rotation, this is your kinetic energy.
Yes.
But if it slides and rotates, in that case, your kinetic energy has both terms.
Yep.
So, okay. If this is a sphere, 2/5 mass, same mass, radius squared, and angular velocity will be equal to speed over r squared. So for the rolling sphere, you have literally more inertia. The coefficient for the kinetic energy, you see, it's 1/2 speed squared. That's what we call mass, and that we can call effective mass. For the rolling object, more inertia.
Oh, the rolling object.
So you can forget about it right now. Don't think about it for 2 more days. And on Friday, I'm going to just start from this slide. Because, yeah. Yes?
My clicker stopped working in this class, I'm not sure why.
Do you know when?
I think it was Monday. Whenever I click something, it flashes orange.
Most probably you may need the battery. Or it was on the wrong channel and you didn't change it when we all did it, because now it's working.
It's channel 21?
No.
41?
That means you came late today in the class.
Yeah.
Because 2 first slides said channel 41.
Okay.
See?
Sorry.
All right. Yes.
Were the office hours that were before this class, did they meet in another room today?
What do you mean? All office hours?
So I went to the basement.
Who? What did you say?
The room was taken, so we went to the basement.
So you were with Michael.
Yeah.
When you were leaving, first of all, did you put a note or some kind of that you're leaving?
There was no.
No.
And the people in the room did not know.
Every time, if anything happening, you should send me an email.
Okay.
I would figure out. I could find what have happened. You know. So.
Are we allowed to miss one lab to go to the office hours there now, or?
You actually allowed to miss 2 labs.
Okay.
We're going to be doing 8 labs now. Yes, no, 9 labs, and 7 best lab scores will be used for the final. Yeah, oh, thanks. Yes.
I have a question.
Yes.
How can I decide the central?
The centripetal acceleration.
Yeah. The top point and the.
You have to draw a free body diagram.
Yeah.
Yep. Well, the free body diagram for,
For the top or for the,
well, let's say for the top.
for the top it has,
So what are you looking for in the end? What's the question?
the question asks, when the pilot is at the lowest point of the velocity, is apparent weight.
Apparent weight. So let's say first recall, what is an apparent weight? What is it equals to the normal force. So basically you need to calculate the normal force acting on the pilot, which means you need to draw a free body diagram for the pilot. For the pilot.
The pilot has a mg point down
And
and n point out.
at the lowest point, the pilot indeed has two forces acting on it. Force of gravity pointing down and the normal force pointing up. How does centripetal acceleration point? Yes.
It points
Exactly, it points up.
at the
So,
lowest point, it points up and
so you have one force directed down, one force directed up, and acceleration directed up. Now you need to write the Newton's second law. Can you show me?
at the lowest point the n points up.
Yeah, but that's a picture that only first step. The free body diagram is just the first step. The second step is writing Newton's second law for that pilot. So I don't see it yet. So can you write the Newton's second law for the pilot? That's not the Newton's second law. That's just a definition of what we call centripetal force. Centripetal force, that's what we call m times a. That's correct. But according to the Newton's second law, m times a is equal to what?
M times a equals to net force.
Net force. And net force is equal to what in this situation?
At the lowest point of the loop. So
Well, what is net force?
net force, I just don't know, is n bigger than mg or mg bigger than n?
How would it help you?
Sorry?
How would it help you?
It will tell me the F net is mg minus n or n minus mg.
No. Can you please take this? Thank. It doesn't relate. It is not related to which is stronger. You have to choose positive y direction, and we choose it always up. And relative to that direction, some arrows should be positive and some arrows should be negative. You have two arrows pointing up, A and N, and you have one arrow pointing down, which is mg. So now we can write the Newton's second law.
If accelerate is points up, that should be n minus mg.
That is correct. Now you can solve it for n. That's what you're looking for, normal force. So
Do we know? Thank you.
just put it on the table. So you have to solve it for the normal force. You don't need this.